So have we discussed any fusion of machine learning, quantum computing yet, or have we just talked about quantum computing?
I should have done, you should do the QCNN.
I have both.
Oh, okay.
I have both.
I should have probably.
No worries.
I don't know whether they remember.
All right, let's see. Oh, took a second. Okay. So. Cool. So just to give you guys a reminder of the fusion between quantum computing and machine learning, essentially how it works is we have quantum gates, if you guys recall, which are essentially unitary matrices, but you can think of it as we're basically rotating qubits, like when you really boil it down. So instead of having classical weights where you have some number, you're multiplying it by some learnable weight to get some output. You can think of quantum machine learning as you have some information that's encoded into a qubit by some way. Let's say by a rotation, we rotate a qubit 25 degrees and our number of interest is 25 degrees. Then we learnably rotate the qubits further and entangle them so that our output minimizes some loss function. So the weight is analogous to the rotation in the case of quantum machine learning. So this first project is actually the project I did in this class. So maybe it'll give you guys some inspiration. I had no knowledge of machine learning or quantum computing, but you know, things are very flexible in this class, which is very, very cool. And you can actually learn stuff. So you guys covered CNNs, right? Otherwise, I won't go into detail. And just as a reminder, this is the input data. And then this is your filter where these are learnable weights. And essentially, we're multiplying each number by the corresponding filter element that it's covering and summing everything together. This is just a regular CNN. So before I get into the quantum stuff, when we have multiple channels, for example, a red, green, blue image, you can think we have all the pixel values that are red, all the pixel values that are green, and all the pixel values that are blue. When we have multiple channels, essentially the filter just is more elements and it extends through all your input data. It's just a generalization. And this is interesting, for example, the first version of AlphaFold, which, finds the lowest energy configuration of proteins via machine learning, it uses CNNs to do so. So there is interest in the chemical world. And, Greg obviously just mentioned his project, which hinges on the CNN.
So we can eventually have a quantum AlphaFold.
Right, exactly. And so that's something that I haven't put aside yet. Maybe in the future, I'd like to do some work with it. So quantum convolutional networks, I'm going to skip a lot of the animations here. Quantum convolutional networks have been a thing for the last 4 or 5 years now. And I would argue it's one of the most popular quantum machine learning analogs for a variety of reasons I won't really get into. But essentially what we noticed when people have data with multiple channels, they're not extending their filter through all the input. And instead what they're doing is they're doing a quantum circuit on one part, a quantum circuit on another part, and a quantum circuit on the other part, and they're adding them all together. And classically, while this would be identical, the problem is when doing the quantum analog, in order to get your output, what do you have to do? You have to do a measurement, right? And as we know, when you measure a quantum system, you lose information inherently. So if we're trying to learn information between channels by taking multiple measurements between the channels, we're going to lose a lot or all interchannel information. And so there is one group that essentially what they do, they just have one big quantum circuit where they do everything at once. And you can see it's kind of large. We have 12 qubits here, right? So the reason people sum them is because it gets very expensive. The more input data you're trying to cover with one filter, then you're going to need more qubits, right? Which is problematic. So I know you guys are brand new, so I'm not going to get into a lot of the details and the math for how it works. But essentially what our method does here is it encodes, let's say we have a 3x3 image, right? And we want to pass a 2x2 filter over it. This is the filter, and we scan this way, right? So At one time, we're going to be needing to do math on 4 pixels at a time, so 4 numbers. So that's what we have here. We store the first number in some angle right here. So like, for example, if the value of this pixel is 0.97, we'll rotate this qubit by 0.97 pi. Same for here, for whatever the next value is, and so on. Then this unitary block here is some learnable rotation. Sometimes people even choose random gates to do random rotations, and actually we see that also can lead to improvement. But the point is, people stop here and they measure and then they keep going. However, what we find is actually when we garble all the information together, that conserves all the interchannel information, or a great portion of it. So essentially what we do is we have gates where we can think of depositing information onto this extra qubit and then re-encode data again, deposit what we have learned from the unitary onto this extra qubit, and we keep going here. And then we just measure the output on this extra qubit where we have been depositing what we have learned without really getting too much into it. And so let's look at how this changes the results. So just to give you an idea on what we're working with here, very simple CNN. Imagine this is your filter, and everything's the same as a regular CNN. We have our input data, and we pass our quantum version of a filter over the input data, and we get one output just like a regular CNN, and we pass it to a fully connected network to get our output. So what's actually the result of this? First, let's talk about the synthetic data. So 10 classes of synthetic data we created, where each of these grids are random numbers between 0 and 1, except the red one, we add 0.05. So on average, the red grids are going to be between 0.5 and 1.5 of random numbers. And the blue grids are going to be between 0 and 1. And obviously, this is not a very interesting data set, but the reason is we choose our classes such that for the first one, the first 3 are, these excited channels. Third class, these back 3 are the excited. And essentially that means our predictions that we need to make, all the information is stored into the interchannel relationships where this one set has been excited by adding the extra number. Over here, this specific set has been excited. And so by pushing all the important information relative to our prediction into how these channels operate with one another, we can test other models to see, okay, how much information are we really losing when we're doing these individual measurements for each channel and summing them rather than incorporating them all at once. And so this control is how it's done in the literature. And you see it actually doesn't learn anything whatsoever. It has flat accuracy, no matter what. And then all these 4 methods are methods in the paper that Greg and I have. And as we can see, for this synthetic data, we approach 100% accuracy, while the established method is just it's impossible to learn anything. So let's actually move to a more interesting data set. And this is the CIFAR-10 data set for image classification, if you've ever seen it. So these are very low resolution images of 10 different things. Here's a cat, a frog, a ship. And actually, this is 28. No, this is 32 by 32. And in the model, we actually scale it down to 10 by 10. So honestly, I can't even tell what they are, but the models are able to, which is interesting. And we see here, 3 out of 4 of our methods outperform on predicting what these images are compared to if we were to look at the red channel individually, the green channel and the blue channel all individually. And so in terms of the numerical performances, we see that it achieves state-of-the-art accuracy on this benchmark data set, which is very cool. But the important thing to note is that it does so while being cheaper than the other established methods that try to incorporate all channel information at the same time. And so you'll see here by circuit width, that just means the number of qubits that you have. That's just terminology in the field. And by circuit depth, I don't know if we talked about circuit depth. That's just how many successive operations do we need to perform on our qubits? Because as you perform one operation after another, you start to lose information over time. For example, you know, if your qubit is in a superposition of the 1 state and the 0 state, naturally we know things like to relax back to the ground state, right? So you're kind of on a race. You want to finish the job as fast as possible. Otherwise, you're going to lose your information. And I say fast as possible because, you know, it takes time to execute a gate. So both number of qubits being high is not good, and circuit depth is not good either. So we want minimum of both of these. And we see this established method right here, which we beat in terms of accuracy. Our method, for example, has a shorter depth and significantly fewer qubits than what's already been done in the literature. And so the next steps would be to actually try to apply this to, you know, something like an AlphaFold, a mini version of AlphaFold. And that's something, if anyone's interested, I'd be happy to, you know, work on a project sometime in the future to do that. As Greg polled, not many people have much knowledge of biology, and that includes me. So, you know, but if anyone wants to learn, you know, I'd be happy to go down that adventure with you guys. And so that was my project for this class. We submitted it like a week after the class ended, and it turned into a paper in a Springer Nature journal. So that's pretty cool. And so also I want to talk about the next project that I actually submitted a few weeks ago. And the reason I stopped there and switched to this project is because I wanted to, you know, do a project that more specifically focused on harnessing a quantum advantage that's, you know, mathematically demonstrable, because, you know, that's the fun part of quantum. And so, you know, you guys have done the machine learning section, and especially with deep neural networks, you know, everything's matrices, right? Everything's multiplying matrices in one way or another. And we know classically, if you multiply an n by n matrix with an n by n matrix, it will take n cubed operations. And to see that, it's not very hard. So let's say you have a matrix A, B, C, and D, and you want to multiply it with A, B, C, and D. To do this, you know, n by n by n by n, you're taking a cubic number of operations, because what we need to do, multiply this by this, right? But in order to do this, we need to add these numbers and add these numbers, right? So that's one dimension. We need to add n numbers here, right? And so that will give us one output. So we need to add n numbers, n squared times to get all these outputs. So essentially there are 3 dimensions that we need to take account for when trying to find how complex these operations are. And so this is a very hard number to beat. So there are ways to reduce how complex these the math is, but essentially they're not very helpful. I found this out because I figured, you know, PyTorch and TensorFlow, they must be doing the best possible work, because, you know, everyone in the field uses them. They must be doing it the most efficient way. And I find out, well, there are some tricks. They still do it the n cubed way. And I was very confused because in 1969, there was a subcubic method to this approach. And then every year, someone publishes a more efficient method. Even just last summer, there was a n to the 2.37. And, you know, not to denigrate anyway, but they're all scams, actually. Because if you're not familiar with this big O notation, any constants that lie, they're called prefactors, in front of this n cubed, they just get hidden in the big O. And it turns out the prefactors in all of these algorithms are so large that you need like more atoms in the universe to calculate your matrices. So they're not really useful, right? But the cool thing is, with a quantum computer, we can achieve n squared, which is kind of like, that is the lower bound, because the output of a matrix will have n squared entries. So it is impossible to go lower than n squared. That is the holy grail of, you know, calculating matrix products. And if you think of the implications in the machine learning world, right? Going from one, say you have a weight matrix that's 100,000 entries, right? And you increase it to 1 million. your math isn't going to be 10 times more difficult. It's going to be 10 times 10 times 10. It's going to be 1,000 times more difficult, right? So like, just imagine these trillion parameter models such as GPT-4 and, AlphaFold. Imagine these models where they're literally hundreds, thousands, and billions of times faster to train than they currently are, right? Maybe you could train GPT-4 in like 10 minutes, right? So that's why this is very exciting. And turns out for quantum, we can achieve this. And so what this project does is it calculates matrix products with complexity n squared. But as you know, quantum computers have errors, right? If someone in our group, Randy, he mentioned that he used to work at a quantum computing company. And if you left the window open where the quantum computer is, that's a fireable offense because of how sensitive they are. A cosmic ray will just destroy your whole calculation. So they suffer noise and errors. So what if we can compute matrix products n squared for the bulk of your network, then pause your progress and continue on a classical machine? Now, as you may have seen from, the previous quantum circuits, it's very hard to see the relation between these qubit rotations to, actual numbers that we use every day, right? And that's because it's a huge abstraction. So it's not intuitive for how we can pause our progress. It's not like we can take the rotation angles of our qubits and call these the weights. It doesn't work like that, right? So that's what this project aims to do. I'm going to skip a lot of the scary looking math.
Yeah, that would,
Yeah?
yeah,
Okay, well,
I find this interesting.
okay, all right, well, so,
Yep, we already saw this also.
oh, did they? Cool.
So they remember.
So this is called the Hadamar test, and you guys have seen it before. And so this allows you to calculate the real part of this expectation value. You can also calculate the imaginary part very easily by putting an extra phase gate, an S adjoint gate right there. But anyways, so one thing to know, in matrix multiplication, it's essentially dot products, right? Because for this first entry X, we need the dot product of this vector and this vector. So you can think of every entry in the output matrix is a dot product of vectors. Well, what do we have here? Pretend this U isn't here. You can think of this inner product of here. In terms of dot products for quantum computers, let's say you have vector 1. This is the inner product, the overlap between vector 1 and 2, which is just a generalization of the dot product, that's not discrete necessarily. But the cool thing is when we have a qubit-based system, they are the same thing because they're discrete. And so essentially, using the Hadamar test, we can calculate dot products very efficiently. And so we have this pesky U right there. And if we want to calculate the dot product of any two vectors, all we need to do is choose our unitary operator such that it evolves this state into the vector that we want. And then what we have is, you can see the derivation. If we choose our state in a special manner, we're able to get the dot product between one vector and the other vector. And so in the context of machine learning, one vector is going to be our input data, and the other vector is going to be learnable weights. So in particular, if you see this circuit here, this unitary gate is the unitary gate that encodes your input data, whatever it is, and you're going to see what it is shortly, into this set of qubits. This line here denotes a larger register of qubits. You don't need to worry about how this U works right now. But assuming we have some matrix that encodes your input data into this set of qubits, what the novel part here is that we can conditionally unencode it half the time, and I'll talk about that in a second, and then encode some learnable set of operations that we can think of as the weights. And I say half the time because we have a Hadamar gate on the ancilla qubit. And because we're doing a controlled operation down here, it's only unevolving the state half the time. right? It's a little weird to think about, but essentially what that allows us to do is on the same register of qubits, we're holding both the input data and our weights at the same exact time. And when I say weights, I actually do mean weights in the same sense as classical machine learning. And the reason is because, so in this case, when we're encoding our data, we are encoding our input data into the amplitudes of that state vector. And what I mean by that is, let's say for 1 qubit state, we, by coincidence, our input data is 1/√2 and then also 1/√2. On 1 qubit, we have stored 2 pieces of information. So this is 1 qubit, right? If we have a 2 qubit state, we are actually going to be able to store 4 pieces of information. 1, 4, 1, 4, and 1, 4. And the reason is because here there's only, a 0 or 1, right? But down here, we have a 0, 0, a 0, 1, a 1, 0, and a 1, 1. So as we start to, add qubits, we can store an exponential number of floats as the values of this very complex wave. And so if this psi here is just a vector of all our floats that we want to store for the input data, we can actually generate a random vector phi, and I do mean random to start with, such that it will be like A, B, C, D. And because we're taking the inner product, we're directly multiplying A with each element of the vector with the other one. So if anyone has any questions, stop me, because it's a little crazy to think about. But essentially by doing this, we are literally doing classical machine learning, just in a way where we are excluding the first part of regular matrix multiplication, where we have to add all numbers individually. Because you remember the dimensions for why it's n cubed is because we have to calculate n squared entries. But for every entry of those n squared entries, we need to sum n numbers. The cool thing about quantum, we don't need to sum those n numbers because it's literally doing it in one step via the superposition and entanglement of qubits. So I said a lot of fancy words in math there, so please stop me if you have any questions.
But that summarizes quantum advantage.
Right, and so, like I said, the reason you might ask, what's the quantum advantage of the first project? And the answer can be a little more nuanced, like there are papers that suggest doing quantum machine learning and that way can generalize better to unseen data. I would say it's slightly hand wavy, but like for this is like mathematically proven quantum advantage, right? So that's what makes it very exciting. And so I also do a CNN except for this project, just because it's easy to talk about. And we apply it to toxicity prediction. So essentially what we do is we take a smile string, which you guys are familiar with, and we encode each element of the smile string to a binary vector. Without getting into the exact details of how, unless anyone's interested, if we encode each character into a binary vector and concatenate them all, so you just have a big grid of ones and zeros, then we're able to pass our filter over this grid of ones and zeros, but we can skip a lot of the steps. Not because it's quantum, it's just because classically there's no need to do this, because this part isn't very expensive, except running a circuit quantum mechanically, you want to save as many resources as you can. So, for example, if we have this grid of ones and zeros, you'll note that red and green here, they're the same exact 1, 0, 1, 0, 1, 0, 1, 0. And so why run both of them? They're going to give us the same exact result, right? So that being said, for 2x2 filters, there are exactly 16 different combinations that you can arrive at. Only, no matter the size of your input data, right? And 15 because if you have all zeros, you don't need to run it at all. So in our case, the smile strings, the grid's like 400 by like 57 or something. Normally that would take 22,000 quantum circuits. That's what people do in the literature. This takes 15. So like, you know, that's why we want to prepare it with binary features. And there are other reasons, such as it's easier to pair quantum states with that are sparse, but you're not going to get into that. And so, go ahead.
How do you make the grid?
Yeah, so actually I have a little bit on this page for how the grid is made. So for every character in the smile string, you convert it to a length 57 vector. And so
And is there one hot encoding for the number of potential?
it's one hot encoded. The whole vector is not one hot encoded, but specific regions are one hot
Like
encoded.
it's 57 because there are 57 potential different characters, and you assign one.
No. So it's 57 because that's just the number of features we use. And then the one hot encoded part, let's say that there's only possibilities for carbon, nitrogen, oxygen, right? We one hot encode just that section. So 1, 0.
Yeah. All of that is 55.
Right. So, okay, yeah. And
Wait, so is each individual feature one hot code?
yes,
Okay.
yes. And there's not a lot of details and nuance into this. This is just a method I found in the literature when I was looking for, okay, what are some ways to encode binary information? So for a CNN particularly that has been established and works well. And so what we're predicting, I'm not a big bio guy, right? So, you know, you guys might know more about this stuff than I do.
Wait.
Yeah, go ahead.
So you're like the first, whatever that is, like 15 inches.
Yeah.
Are like literally the string converted to vector. Right? And then you're appending these
Yes.
chemical properties on the end of that.
Yes, exactly. Yeah, but any more questions? Go
And
ahead.
extended.
Right.
string. It's interesting.
I wonder if you would benefit from having two different representations processed individually.
Yeah, it's totally possible. I just didn't put too much time into it because that's not, you know,
Because it's one filter.
Yeah.
That's being applied to something like a bracket as well as something like molecular weight.
right. I mean,
I mean, if it works, it works.
Yeah,
It's
it
not
works.
very intuitive.
I can't remember at what point I said it in the paper, but I made some argument like, you know, this may not be ideal, right? But that's beside the point, right? And so this is actually the task at hand. There's this data set called the Tox21 data set. It's about 10,000 molecules. And essentially all these smile strings are labeled binarily, like 1 or 0. Is it active to this receptor? Yes or no? And then so on for 12 different receptors. And so our task is binary classification. That's what we're trying to do. And so this is the full architecture, just for your own information. We have our big grid that's a smile string, and we pass our quantum filter over it, except instead of what you saw from the last project, this quantum filter works so it calculates products with n squared complexity. And so after one filter, then we just pass it to just a regular network, a regular classical network. And so, like I mentioned, the part where we can pause our progress and continue, that's called transfer learning, if any of you have heard of it. And so there's a lot of work from classical to quantum transfer learning, but there's not a lot of work from quantum to classical transfer learning. And like I said, it's because it's such a black box. You know, when you're dealing with just qubit rotations that are learned, it's very hard to find an analog, right? But the reason we can easily find an analog here is because, like I said, we're just multiplying vectors, right? Where we already know what the values are. So essentially, remember, this is our input data, and we unencode it half the time. This is just a learned set of operations that produces some vector that's being multiplied by the input multiplied to the input data. So essentially, all we need to know is find out what vector is this creating here. And that could be expensive if you have to do it every time, but you only need to do this when you're ready to transfer the network. And that's only going to happen once, no matter the size. So that's not a large concern. And so the whole workflow is as follows. You take your SMILE string, you featureize it with what we just talked about. You do the quantum convolution where we're using n squared complexity. Pass it to the rest of the network to be a classic big process. You make your prediction and you keep going. You keep, training your model. And then at some point when, let's say, your accuracy is starting to converge, but you're worried that errors from a quantum computer are going to, ruin that convergence. You did a lot of the hard work, but now you want to get a fine-tuned answer. You say, stop, okay. I've had enough quantum advantage for the day. And let's figure out where I left off by finding out what vector this operator produced. And we literally, all we have to do is, once we derive the vector, those are the weights. Because like I said, this pairs the vector that we're multiplying one by. So as soon as we derive it, we have the exact weights we need essentially. And so we plug those into a regular CNN and just continue the process with, of course, n cubed complexity. But the point is, we already made a lot of, the hyper efficient progress in the first place. And so, just for a little validation, you can see here that this process transfers the learning progress perfectly. Like there's no disruption, right? And that's because the theory says there's no disruption. However, if you don't do it properly, you're going to see these huge spikes. For example, if you just took all your weights except the one from the quantum part and just reinitialize them, your training progress is going to be screwed because you didn't transfer it properly. So essentially, this is just validating that this method transferred the weights. I mean, it's mathematically. And then finally, for all the results, we can see that the quantum part performed just as well as a fully classical network. And that's all we need, because we're not looking for an explicit quantitative advantage in terms of accuracy. We just want a hyper efficient way of doing so. So this shows that our way of doing so still maintains the same level of accuracy as the classical network. I understand you guys are out of time, but that's some work that's going on in the Batista group and for this class too. So